After the success of the Global Photonics Economic Forum in Malaga, powered by more than 300 human beings, it's now time for the Optica Online Industry Meeting on Photonics-enabled AI. Artificial intelligence is pushing the limits of conventional electronics. 2 new data centers open in the US every week, adding to 1,200 sites already operational. But AI data centers may soon consume 12% of all US electricity, up from just 4% in 2023. Photonics has emerged as the key enabler for next-generation AI hardware, boosting processing speed, reducing energy consumption, and unlocking massive scalability. Photonics is not a side story, it's the only way forward, because without optics, AI's energy demand will bankrupt utilities and households. Without lasers, there's no cloud, no global communication. On Tuesday, October 14th, starting at 10 a.m. Eastern, that's 4 p.m. in Central Europe, we'll gather leaders to explore how photonics and AI are converging. We'll debate how to integrate photonics with AI hardware at scale, and how to overcome data throughput and latency bottlenecks. We'll explore new business opportunities in neuromorphic computing, optical processors, and supply chain collaborations. Our speakers include technology integrators from NVIDIA, Lumentum, Celestial AI, Ipronics, Pincetto, Quant, and Lumai. We're also joined by technology enablers from ANSYS, VPI Photonics, Quantify Photonics, and PIC Advanced. Free attendance is made possible thanks to generous backing from these corporate sponsors. They give the conversation value. It's a live meeting in Zoom with a replay later on YouTube. Now let's get started and see who's joined us for the live discussion.
Hello everyone, good morning, good afternoon, good evening. Today we are global. We have people from the US, from Europe, from Asia, all of us targeting perhaps the biggest challenge of our industry. The market, all of you are smiling because the market for AI in data centers is really buoyant. Something that I have never seen before. As I said in the video, every 2 weeks we have a new data center in the US, and one of those hyper data centers can consume the same power as 400,000 homes. So the AI is driven by power, and we're here, all of us, we're here to solve the biggest challenge of AI. The current power demand of AI are unsustainable, and only all of you can solve it. Today perhaps is the most important meeting, and for that I would like to introduce the person that put all of this together. I would like to introduce John Pugh, but before I do that, I would like to welcome everyone to an event surrounded by sponsors. An event that is for free, as I said before in the meeting, because we had the support of our members today. Our sponsors today are Legend Tech, offering silicon nitride photonic integrated circuits all the way from Switzerland. New Photonics, one of the key companies offering record-winning speeds in interconnects and connectivity. PIC Advanced, coming all the way from beautiful Portugal. They offer already fully featured pluggable solutions and also packaging services. VPI Photonics, one company that offers software simulations that you can design at peak in the same way that you would design an optical network. Polariton Technologies, coming all the way from Switzerland, offering the best possible, the highest possible transceivers based on plasmonics. Quantify Photonics, a company that is now one of the record-winning solution providers for metrology in ultra-fast interconnects. One of the leading companies in transceivers and interconnect and connectivity solutions, a global company, Axelink. Also Vanguard Automation and Micronic, offering 2-photon polymerization technology to do packaging of integrated photonics. And last, but definitely not least, ANSYS, one of the key companies in design and simulation software. Thank you very much for our sponsors today. John Pugh put together one of the best agendas I can see for a topic like this one. We have, as usual, 2 teams. The integrators that are here offering full solutions and they have challenges for the customers and suppliers, and the enablers who are here with a part of the solution that can help the entire system. The integrators today are NVIDIA, Lumentum, Celestial AI, Ipronics, Pincetto, Quant, and Lumai. The enablers, ANSYS, BPI Photonics, Quantify Photonics, and coming all the way from Portugal, one of our favorite companies, Peak Advance. This is one of our meetings in the series of online industry meetings. Write in your calendar 28th of October. This is a very important date. It's an online industry meeting on augmented and virtual reality. And of course, many of you were in Malaga last week. We keep meeting face to face and we love that. Our next meeting is next week in Sunnyvale, California, hosted by Juniper or PEC Summit, Photonics-enabled cloud computing, organized both by Optica and Advanced Photonics Coalition. I hope I see some of you in Sunnyvale. Remember that we do this not because we love organizing events, but because we want to provide the best potential value for our corporate members. If you are not yet a corporate member, all you have to do is to go to optica.org/join corporate. We need you. If you don't become a corporate member, we really may have a problem. Please join us. Join us, keep growing. We need to keep growing this fantastic community. And also I would like to remind you that now we have the largest database of market reports for our members. Optica.org/market reports. All our corporate members have access to a long list of market reports, commercial market reports, presentations, videos, tutorials, all the content available for you for free. Today is all about photonics for AI, but let me allow 1 minute of your time to say hello to the YouTubers, because this meeting is also live streaming YouTube. Hello YouTubers of the world. If you have any question during the meeting, all you have to do is type it in the chat and I will read it in the room. And this is of course also valid for the people here with me in the Zoom room. This meeting has to be very interactive. If you have any question during the event, write it in the chat. The microphone will be coming to you and you will voice the question yourself. The most important thing here today is to connect. So please write in the chat what you do for others and others can do for you, and use the chat for private discussions, because at the end of the day, that is what it's all about, right, John? Congratulations on the fantastic job you have done putting together, in my opinion, the best possible agenda for photonics for AI. Dr. John Pugh, the floor and the attention of everyone is yours. What's going to happen now?
Well, thank you so much, Jose, and hello, everyone. So I'm delighted to be co-moderating today. It's an exceptionally exciting topic, which is shown by the number of people who've signed up today, well over 500 people. So I'd like to thank in advance all of our speakers for joining the meeting and being prepared to answer all of your questions. So please keep them coming, as Jose says, in the chat and on the YouTube room, and we'll welcome you to unmute and join the conversation. So let's get to it. To kick us off, I'm thrilled to welcome Liron Gantz from NVIDIA. Liron leads NVIDIA's Electro-Optics NVEO group and is a principal research scientist driving the company's silicon photonics and co-packaged optics programs, work that directly underpins low latency, high bandwidth networking for AI at scale. Liron, the floor and the attention of everyone is yours.
Thank you very much.
An NVIDIA and sometimes personal view on how photonics is accelerating AI systems currently and what will happen in the future.
Today, I'll focus on our research vision of optics interconnects. So these concept represents where we think technology could go, but not necessarily what will appear finally in the product. So having that in mind, let's start. And let's start by defining two domains. So the first domain is the scale-up. And we can think of the scale-up as connecting a lot of GPUs with high bandwidth connections, and they can operate as one big GPU or one super node. Now, physically, you can limit these devices to one rack. And today they are dominated, the connection is dominated by copper. The other domain is the scale out, and there we need networking. So we can connect a lot of racks or entire data center, and these connections can spread from meters to kilometers. And what dominates these connections are optical transceivers or pluggable optics until a few months ago. So what's the situation today? Let's look at pluggable optics. So pluggable optics, and you can see the power consumption numbers according to these references. And the main issue, the main two limitators that limits our power or driving up the power consumption are first the number of bumps, which then translate into pin density. So we have limited number of bumps between the ASIC and the organic package. And the second is the distance. So the distance between the ASIC and the optical engine, which makes the signals go a long distance, which then translate into losses and which then translate into heat that we need to dissipate. And when we check these power consumption numbers, we can see that this is in fact unscalable. So we switch to co-packaged optics. And in co-packaged optics, what we've done, we've taken the optical engines and we put it closer to the ASIC, put it on the organic package on the MCM. And just by doing that, we reduce the power consumption by 60%, but we're still bump limited. So, for example, NVIDIA used the TSMC co-packaged optics or a COUP process, and this is an example of another concept that I want to introduce you, and that is narrow and fast, which means we are using one wavelength, but we are modulating it very, very fast, 200G and maybe even 400G and so on. So how can we scale from here? So first of all, these are, of course, the NVIDIA products, the Spectrum X and the Quantum X. These are the two CPO products that NVIDIA announced a few months ago. So how can we scale from here? So there are a few vectors that we can scale across. So first of all, it's the time domain. So we can continue to increase the rate from 100 gigabaud to 200 gigabaud, 400 gigabaud, so on and so forth. But if we look at what we are getting, so we are getting diminishing return with regards to the energy efficiency. We can continue along the amplitude, so use higher order modulation. So we already using PAM4, we used to use NRZ, now we're using PAM4, we can go to PAM8, we can go to QAM, but then again, we are getting diminishing returns with regard to the signal to noise. We can use polarization, but polarization only gives us a twofold increase. The other option is to do space domain multiplication. So, but there we are limited by the size of the fiber because we cannot get the fiber closer beyond 80 micron, or maybe we can push it to 60 micron. Then the fiber starts to lose its fiber properties. And the final vector is the wavelength domain. We can increase the number of wavelengths. And if you look, I didn't draw a brick wall, but I'm actually it's kind of cheating because actually I dumped the problem on someone else, which is okay if they can solve the problem better than you. And the people I've dumped the problem on are the laser manufacturer. So I'm counting on the fact that laser manufacturer can manufacture lasers with a lot of wavelengths. So these are the main vectors. So the upper two are an example for the narrow and fast, using one wavelength or a limited number of wavelengths and modulate them very fast. And the last two are the example of wide and slow, which means we are using a lot of wavelengths or a lot of parallel lanes, and we are driving them in slower rate. And I would advocate that this is actually the way to go to get power efficiency. But in order to get that, we need to go to more advanced packaging. And this becomes crucial for efficient optics, which we already saw because this is what we've done in the co-packaged optics in the current solution. We've done more efficient optics on the expense of much more complex packaging. So in order to go to slow and wide, we need to go to higher, more complex packaging like 2.5D optics, in which we add an interposer between the optical engine and the organic package. And we can increase the number of bumps. And if we increase the number of bumps, we get higher density. We can go with lower rates. We can add more modulators or more compact modulators. So in our case, that's one of the reasons that we've started using ring modulators, because they're quite compact and small, and we can scale them. So this is the way it's going to look. Yeah, this is the comparison between the CPO and an MCM today, and silicon and how it's going to look on the silicon interposer. So the optical engines are much smaller. And as I said, we need denser modulators. And this is a conceptual way of how this link is going to look like. But again, this is not set in stone. This is just a conceptual way of how this link will be. So we'll have a lot of wavelengths, a lot of rings on the modulator sides, and rings and a lot of filters on the receive side. So when you look at the comparison between narrow and fast and wide and slow, and there are a few metrics, and I won't get into all of them, but the main message I want you to take is that when we go to narrow and fast, the burden is on the electronics. When we go to wide and slow, the burden is on the photonics. And as a photonic guy, I can tell you that there is a lot of room to improve in the photonics. We are barely scratching the surface, which is good news for our community. And these are just a few ways we can improve. We can do better modulators. Again, not faster modulators, but more efficient modulators. We can improve receiver sensitivity by switching to APDs or including even gain. And this is, of course, this requires advanced packaging. We can improve thermal tuning by improving the heaters themselves or better temperature isolation. And we can improve our designs by using a much more what I call topological protection, which means we are designing devices which are much more resilient to variation in process, which then can translate into less thermal tuning and less power consumption. And of course, from the laser manufacturer point of view, we need to go to, if we want to go to the wide and slow, we need modular comms or care comms or comms in general. So the main takeaways: advanced packaging and multi-carrier can allow trading the electronics to photonics, move the burden from the electronics to photonics. Of course, we need to think of how to do the fiber connectivity when we have so many modulators. We can improve the process variability by doing better design. And if you look at the paper, we just published a paper which describe how we can go to links that are sub-picojoule per bit. And if we do that, then optics become attractive for the scale up, not just for the scale out, which then means it's competing with copper. So that's the main takeaways.
Right, Leron, thank you so much. It's been a meteoric rise for NVIDIA, thanks to the huge increase in, the global thirst for data. The announcement of Spectrum X and Quantum X CPO switches at GTC earlier in the year surprised many, I think, in terms of the acceleration towards CPO from NVIDIA. What guidance can you and NVIDIA give the photonics community publicly to be ready for the next round of big NVIDIA announcements? And what should they be working on to help you continue with your current rate of advancements and ultimately partner with you?
So again, I represent what we think will be on the research side. I cannot speak for the product side, and of course there are other people that can talk about this better than me. But I presented these two main approaches, which is the narrow and fast and the slow and wide. And if you ask me, this is my personal opinion. I think that we have a few more, maybe one or two more generations we can go to the fast and narrow, which means modulators like lithium niobate or even plasmonic can play an important role. But I think that at some point we'll have to switch to the slow and wide. And so this is the main direction I can give for the industry.
Great. We have a question from Andrea Bez in the Zoom. Would you like to unmute and ask your question, Andrea?
Yes. Can you hear me? I don't know.
Yes. Yeah. Hear you well.
Yes, thanks a lot for a great talk. I mean, with the with Spectrum X and Quantum X, in terms of performance that you're getting and the ability to interconnect, millions of GPUs, what's your view then on these OCS, pure optical circuit switching methodologies to address this interconnect and this kind of low power or highly efficient power architectures?
So this really depends on the architecture of the network themselves. There are networks that I imagine that will require this kind of just optical switching, but they will not replace the interconnect that you see today. There'll be another layer. So I don't see, and again, this is my personal opinion, I don't see all optical switching replacing the interconnect that we do have today. Maybe that will be another layer that you add to the complexity of the networking.
Thank you.
Great. Thanks, Laura. And I guess today we'll hear talks on fabrics and photonic compute even. In terms of an NVIDIA R&D opinion or priority order for optics, where does it kind of run? Is it scale up inside the package, scale out across racks, or even optical acceleration? And what are the single metrics, the metrics that decide those priorities?
So essentially, at the end of the day, it's picojoule per bit. So whatever can get you less picojoule per bit, that's what's going to win. Having said that, when I introduced the wide and slow, we have the potential of doing the same kind of links. And I think co-packaged optics and silicon photonics, these are the enabling technologies for that. And we will be able to do the same kind of links from millimeter scale to kilometer scale. Of course, there are competing technologies. I didn't mention pixels, but pixels are something that people even we are looking at. So again, at the end of the day, it's picojoule per bit.
And finally, I guess on that point, you argue wide and slow 2.5D optics on a silicon interposer gets us below the 0.4 picojoule per bit and multi-terabits per second millimeter densities. Can you give us any insight on the first product class inside NVIDIA that crosses that line?
Unfortunately, no, I cannot. I cannot disclose any.
Answer.
Yeah. Sorry.
Okay, we have another question in the chat from David Sanchez. David, would you like to unmute and ask your question?
Sure. Can you hear me?
Yep, hear you well.
Perfect. Yeah. So one question I had regarding to the laser manufacturing and how it could scale up. I've been reading lately about the CWWDM MSA that was proposed by some partners in the past. Would that be a way to scale the data rate in terms of the wavelength grid?
So that is one way, and that of course depends on the domain. So I can say that in the scale-out domain, there is a lot of room. There is room for interoperability between different companies, and then we have to agree on some. We have to agree on a grid, or we have to agree on spec. Inside direct, you can say I don't see people mixing NVIDIA and Cisco and things like that. So inside direct, there is a potential to do whatever you want. So you can do whatever makes sense. Is that does that answer your question?
Yeah, it makes sense. Thanks.
We have a question from Alan from Ars Optics. Alan, would you like to unmute and ask your question?
Yeah, for sure. Thank you. You mentioned that 2D fiber array is crucial in your to improve your systems. And can you give us some more explanation on that?
Yes. You are right that I didn't address this enough in my presentation. So you saw that if we are going to 2.5D integration, we have to the optical engine becomes smaller. So we cannot increase the beachfront. So where do you put? How do you connect so many fibers in such a small in such a small beachfront? You have to go to 2D. You have to use 2D arrays of fibers. That's our at least that's our direction. Now you can do this with surface coupling. You can do this with edge coupling. It's much more difficult. I'm not saying it's not impossible, but I would bet that if you want to go to 2D coupling, it has to be some sort of surface coupling. And again, I know that a lot of people, when I say surface coupling, are thinking of the grating couplers. Not necessarily, but it's not necessary.
Great, thank you so much, Laurent. In the interest of time, we're going to move on to the next speaker. So I'm delighted to welcome Erman Temirdagan, who's Director of Silicon Photonics R&D at Lumentum. Erman leads next-generation integrated laser and transceiver silicon photonics programs, work that directly touches today's pluggables, LPO, and the path to CPO in AI data center networks. He's authored Lumentum's energy-efficient AI networking work, and his team is hands-on with technologies like external light source pluggables and ultra-high power lasers that underpin emergent CPO architectures. Erman, please share your slides. The floor and the attention of everyone is yours to map current state of pluggables, LPO, CPO, and what's real in deployments today with Lumentum. Thank you so much.
Thank you, John. Hope everyone can see my slides.
Perfectly.
Okay, very well. Yeah, I think Lino made a great entrance to the space, and I'm just going to touch base on more maybe high level things, but it is more short term view of how we can improve the power consumption of the network as a whole, such that we can give life to more GPUs in the network or more training capability, such that the overall system efficiency is improved. So what you see is like an AI network topology, very simplified, showing the GPUs at the bottom and electrical packet switching, connecting all these GPUs together using the scale-out network outside of that gray box. And the key difference between this AI training network versus a traditional data center is that there are no oversubscription. So all GPUs need to talk with all GPUs. So that requires usage of best-in-class components in all of this network. And if you make some proxy networks, you can see the number of components in that network for different AI training workloads, like the famous GPT-4 and GPT-5 is a proxy at the time, just showing that there's a significant increase in number of switches, number of transceivers, approaching to 800,000 transceivers in the network just to build an AI training network. And if you look at the network power, that's upwards of 20 megawatts and a total power of like 100 megawatts just to train these networks. So these are staggering numbers for a data center, even like it's almost the entire data center on some scale. So it is critical to address as much as we can. At Lumentum, we work on the optical side, and therefore the network is a target we can impact. So one way to impact that network is to introduce optical switching in the replacing some of these electrical packet switches. So what you see here is the hypothetical replacement scenario where the spine layer is replaced at the top with optical switching with these large boxes with Purdue inputs that are all fiber in, fiber out, and some connectivity replaced in between GPUs inside the server. So if you just take that into account in terms of just the network side, the scale-out side, and ignore the scale-up, and remove all the electrical packet switches, there's a significant savings in power. And that comes from the fact that, the optical circuit switching is much lower power, lower cost, and is more available for spine today, but it can impact the rest of the network. It comes with a lot of network handling challenges. It's not, completely free for just replacing, but it is one vertical that can be employed. Another vertical is to, build today's pluggables a little bit better, and if not a little bit more better, if you can. And that's a lot of actually, that's a lot of physics and multidisciplinary work that goes into it. I just put some physics and multidisciplinary groups that work together to build a pluggable module, and changing one can affect the other. So there's significant savings, when you build a vertically integrated product. So that there are some advantages in that. Without going into details, here's an example for 200G per lane silicon photonics flip chip module that shows the open eyes on the bottom left of the figure, and bit error rates reaching down to error-free levels at this high rate, which is narrow and fast path of scaling. You can see the copper pillars in zoomed in pictures and the connection to the PCB. So in general, it is a direction towards more levels of integration without really breaking the bank or changing the form factor. Obviously, going higher speeds and going the next generation, it requires a lot more advances, as well as some power reduction by removing some portion of the digital signal processor And those are things that we are working on to make it more energy efficient. So if we then look at the same chart we just looked at, but adding on top of the electrical packet switches and electro-efficient optics, there's a significant savings in network power there. And if both approaches combine, it's a massive savings. But obviously, this assumes that the entire network is replaced with these new class of transceivers and optical switching elements. Instead, that can be partial, and that might be the more resilient way to build the networks. And scale up, which goes between GPUs, will only accelerate this. And I think there's a lot of work to be done in short term and long term, as we have seen. Thank you.
Great, thank you so much, man. Thank you for joining and giving us an overview of what you're doing at Lumentum. So you cite near error-free at 200G lane PAM4. What link budget and temperature assumptions are required to keep that post-forward error correction clean in production, and I guess not just in R&D labs?
Yeah, one of the requirements to keep the bit error rate levels low is to be able to access very high SNR, and temperature is one of your enemy in that scenario. So temperature environment of the overall link is quite important. And another one is the overall signal integrity between the digital signal processor to TX side and then back to RX to the DSP. So that whole link has to be clarified. There are a lot of noise terms that enters into the system, and one of them is laser intensity noise, and that has to be controlled as well. So that's one of the noise terms that really gets affected by temperature. So I will say temperature and signal integrity are two key factors.
And I have more of a kind of overview question for you. What industry collaborations do you think need to happen for AI and cloud workloads to maintain this unprecedented pace?
I think there's a lot of innovation that's being kind of expected, but there is a very limited amount of reliability hours and reliability work that we can conduct given a new technology. So it definitely slows any introduction of any new technology to the market, whether that's something we are working on or some other companies working on and collaborate on, because reliability is the utmost importance here. Like dropping a link in an AI training network is much more costly than losing a link in a traditional data center. So focusing on reliability together and finding a way to collaborate on that, it will be utmost important. And also defining specifications and next generation targets earlier, which is very difficult to do. I fully understand that, but technologies take time to proliferate and percolate and improve. So it takes time. Yeah.
Right, and Jose has commented in the chat, that at ECOC 200G per lane PAM4 seemed to be the de facto standard. And for how long? And is this future proof?
It's definitely not, as we have seen historically in optical transceivers. 200G PAM4 is, will be challenged by 300 or 400G solutions. I think it will be a long deployment cycle for 200G compared to what we all initially thought. But at 400G, we have a lot of discussion on whether that will be still at PAM4 or some other metric, because copper is having difficulty with PAM4.
And Steen from Ligentech, would you like to unmute and ask your question in the room?
Yes, hello. Just a quick question on optical circuit switching. Do you see a need for high-speed switching? Because currently it seems there's not really a strong need for that, maybe now or in the future.
So I think that yeah, that needs a definition of the switching speed. If we are looking for a switching speed at the speed of an electrical packet switch, that's very unlikely that that will ever happen. So therefore, there is a penalty on switching speed in no matter which technology we choose to implement. And beyond that, if we can switch faster, that gives the network to be able to reconfigure itself faster and recover itself faster. There are many research papers, talking about how switching speed relates to some part of the network activity. But one of the use cases of this switching is that, as long as you can predict the network with high accuracy, you can prepare for this switching activity. So depends on how well you can predict your network and how fast you have to switch to account for the unknown or unwanted part of that network really will boil down to that. I think the faster is better, of course, but it comes with a price, either in loss or actual cost of the component, or even the reliability, because you're using high voltage switching sometimes, and that component has a lifetime on its own. Yeah.
And final question for Erman at Lumentum comes from Andreas Volker at CSEM Seacraft. Andreas, would you like to unmute and ask a question?
So yes, unmuted. Thanks. You showed very nicely what all this boils down to for the transceiver. And before we heard NVIDIA in general, in the data center, one important metric was picojoule per bit. How much energy do we need? But in the end, then in the supply chain moving downward, we always have to also work with dollar per picojoule per bit. So it's actually a triangle that we have to meet there for new technologies. And on the transceiver side, do you have an updated metric where we are for the next generation? How, what price level do we have to reach to be attractive there with our transceiver technologies and in the supply chain?
Yeah, this is going to be an answer that will not be related to my company. It will be my personal answer. And in the last OFC, Meta mentioned publicly that we are at a quarter of $1, $0.25 per gigabit, and that there's more to come. And I do think there's more to come, because if we break the barrier of 3.2T, 6.4T type of packages, there is a potential for driving the cost to 10 cents a gig type of range. I think below than that, it's going to be quite difficult. There is still a large gap with that number to copper, though. We have to acknowledge that.
Mm-hmm. Yeah, that's going to be interesting how that plays out in relationship to the energy requirements, where there's an inflection there. What energy is too much? Because of course you can drive down the price for driving up the performance.
I can answer that one very quickly. Is that the higher levels of integration generally drives the cost down, but we need to also recognize that these are semiconductor parts. I mean, silicon photonics is less expensive than some other components, but there's a laser piece, there's a fiber piece, and there's a connectivity piece. And as I mentioned, the reliability requirement will only go up rather than go down if we do higher levels of integration and packaging.
Great, thank you so much, Erman. Let's keep this moving. I'm excited to bring in Antonio Teixeira, co-founder and CSTO at PIC Advanced. Antonio leads a team well known for end-to-end PIC design, development, and packaging, including a proprietary packaging platform focused on thermal management, precise optical, electrical alignment, and fiber attach. These are the gritty realities behind Pokeballs, LPO, and the path to co-packaged optics. Antonio, you've shared your slide. Please tell us more.
Hello, thank you, John, and all of you waiting there. As I said, as Papuk said, I'm the co-founder. I've been the team, of course, building an opportunity to control the value chain all over the industry around the integrated circuits. And we have been doing that in a different topics, so ponds, but all the technologies that we are developing and all the strategies that we are developing are also applied to the new products of the next generation of high-speed devices. So we, as you can see on the screen, we have our own opportunities in demand search. Then we have optical design in our lane, and also we do testing and adaptation of the circuits, and also at the same time we do the whole the process up to mass manufacturing. So with this, we think that we can position ourselves as a good partner for design of optoelectronics, advanced packaging, and also produce and help to mass produce the devices that you are looking for. So we have a lot of experience in all the types of systems, as well as even the 2D and 2.5D approaches. So we see ourselves as a platform for the next generation, and we are, of course, open to opportunities. And what we can give is, of course, all the things that we have been developing these 10 years. And what we are asking is, of course, applications and more results and products.
Antonio, congratulations on everything that you are doing. We are really excited of the developments of Peak Advance. We saw at ECOC that many companies needed to go from demo to pluggable, and you are a key partner on that, on providing that link between the pluggable and the demo. Antonio, congratulations on what you are doing, and many companies I know they are interacting with you to make sure the innovation can go into a pluggable as soon as possible so they can show the right form factor to customers. Congratulations, Peak Advance, but let's move on. Today, we go now to the serious part of the meeting. Today, we want to welcome for the first time at an online industry meeting a key company in our sector. They are perhaps one of the most innovative companies in the ecosystem. We are talking, of course, about Celestial AI and how to build, how to destroy, how to break the memory wall with the photonic fabric. Thank you very much, Subai Sahni, for being with us today. The floor and the attention of everyone goes to Celestial.
Yeah, thanks for having me here. So I'm going to talk about what Celestial's developed over the last few years, which is the photonic fabric, specifically targeting scale-up networks. So yeah, as the previous speakers touched upon both the scale-up and scale-out domain. So we are looking at the scale-up where we think the potential for disruption from the photonics industry is actually maximum. So I'm actually going to just jump into our technology directly. I'm not going to spend too much time motivating why we need what we're doing here. I guess Liron talked about that too, in terms of the limitations of current networks, especially pluggables. And so I think it's quite clear that the industry needs to go towards deeper levels of integration to solve some of those problems. So at Celestial, what we have developed is what we call the photonic fabric. It's a full stack technology platform, which means we do not just the PIC, the photonics, we do the full ASIC, which has a full SerDes in it. We build the software stack on top of it. We provide actually a platform where you can take that and package it into your network. But in its most fundamental level, it's basically this is a Cardinal what it can do. So it's actually a network that you can use starting even within a chip or package. It's something that can be integrated directly into an XPU's IP, where we provide a photonic interposer to move data within a chip or between packages or two chips within a package. And then the same network is extensible to actually leave the package and then go to neighboring GPUs or memory. So that, of course, would be the scale up part of things, and what we call scale in is the other aspect of this. This in-package communication, of course, is not something that's in any roadmap currently, but it's something that we think is actually not that far away once photonics really penetrates the scale-up industry. So what do we have inside the technology? We basically we've built. So as I said, it's a full stack solution, which means so we do the ASIC, we do the PIC. So the ASIC is a fully IC with analog SerDes that also has a very large digital component. It's been completely co-designed from scratch with the photonics. So we think we have some of the lowest powers in the industry, less than 3 picojoules per bit, which I think for a co-packaged solution is sort of the table stakes really to get integrated into any meaningful system. It's a very compact design, so bandwidth density is extremely important. Leron touched on this a little bit too, as you get to higher total bandwidth requirements. It's important that the network doesn't limit you in terms of bump count and things like that. So we have densities of about a terabit per second per millimeter square currently, and it's millimeter square because our technology can go beyond the beachfront, so we can integrate our technology directly into an XPU. So the more area inside a package that's allocated to Celestial, the more bandwidth that we can provide. The photonics, we've mentioned this in many other meetings. So we use EAMs, which we believe are kind of a compelling solution for not just providing extremely compact high density modulation, but also thermally stable modulation, which as the integration with the ASICs gets more and more deeply embedded, is a very critical part of the solution. So the PIC also has a fully optimized PDK that provides very good performance. And then the lower 3 parts here are actually something that we've been working with a lot of industry partners. I think it's a place where there's a lot of further potential for collaboration, which is the fiber interfaces. So we have a connectorized fiber solution, but this is something that there's nothing fully standardized, of course, and it would be good where if the industry actually takes steps to provide high volume solutions that are fairly standard for a couple of different connector configurations. Then we use standard, CoWoS-like packaging to be as compatible with current OSAT process flows as possible. And then, of course, a high volume supply chain, which means everything else that other people have spoken about, lasers in particular, but also the fiber interface elements. A quick demonstration of what have we shown so far. So Celestial is about 5 years old now, so we've had several generations of optimization of the technology. So we haven't reached the performance metrics that I mentioned kind of overnight. So our ASICs are optimized in both 4 and 5 nanometer TSMC processes. This is a picture of a AMS quad. This is the 1 terabit per square millimeter density PHY, essentially, that you can integrate into your IP. So it's essentially a quad is 4 channels, each at 224 gigabits per second, and each channel itself is 4 lanes running at 56G, so 4 lambda DWDM. As I said, includes the full SerDes, of course, the TIAs and the drivers for the modulators, all the supply domains, PIC observation blocks, everything is provided by Celestial. And we can get post-FEC BER rates that are very, very small. We also provide the FEC ourselves, a very light FEC that's included in the PHY. There's been a lot of demonstrations of this that's been running, as I said, for multiple generations, where this technology has been fully proven out. So what can we build with this? So a couple of things, actually. So the 2 things on the left are actually what our upcoming products that will be released in the next few quarters. Jose mentioned the memory wall product, which is actually the one here. This is essentially a photonic fabric memory module. So this provides, at its simplest level, an HBM memory with an optical interface, so that memory can be disaggregated. But this chip contains much more than that. So as you can see, there's 2 HBMs in one package, but it also has DDR interfaces. So the HBM can be augmented by much, much higher density DDR, but then the DDR can be cached with the HBM. So it gives you DDR capacities at HBM bandwidths. Also has a PCIe interface and also has a full crossbar switch inside it. So it has some switching capability that can be used to build scale-up networks. One thing to point out, this is sort of the first implementation of a chip that actually completely utilizes the beachfront for electrical purposes. And the optics is right in the center of the SoC, which is probably one of the unique chips in the industry that is doing that. So these 4 blue dots in the middle are actually the optical IOs. And all the edges of the ASIC are used to provide high-speed, serial interfaces, which is exactly what the industry normally needs. We're also building a GPU to GPU chiplet product where there's a die-to-die PHY interface that's to the XPU, and then which is UCIe based, and then we provide the AMS technology to convert that into our fabric. So these two combined can basically lets you build very complicated XPU to XPU networks and XPU to memory networks. Just looking ahead in the future, we're also collaborating with a couple of customers on other products that we think can, they're definitely on our roadmap, and I think can be very, very disruptive in the industry. Again, they utilize the platform strengths that Celestial has in that the technology is extremely compact and thermally stable, and so you can embed it inside of CPU or GPUs or XPUs as needed. So in this example here, again, you can build a multi-XPU package where the serial interfaces between neighboring XPUs are still completely maintained. They can be completely electrical, and the optical networks are behind that so that you don't actually disrupt any of the existing technologies, and you still provide optical I/O to leave the package and build out your network. Just last slide on what we're building using some of those building blocks. So the memory module goes into basically full all-to-all connectivity scale-up networks. So this is an example that we're working with a system integrator where you can take 16 XPUs on one side and use the memory module that I mentioned before and build large appliances on the other side. What this does is it simultaneously provides you a all-to-all connected network. Because that memory module that we're building also has switching capability, you actually get a sort of medium radix switch with very, very high throughput. So this particular example is more than 100 terabits per second in terms of total switching capability or switching bandwidth. But it also gives you disaggregated memory. So in this case, it's 33 terabytes of memory. 1 terabyte of that is HBM and 32 terabytes are DDR. But as I said before, you can actually cache the DDR with HBM. And so you can get that DDR capacity with HBM bandwidths. And finally, you can use all sorts of or perform several of the standard collective communication actions that you need, broadcast and reduce, things like that. That's all implemented in the network, so that it's something that can be used kind of right off, coming out of the box, and it provides you all the features that a regular scale-up network would have. And with that, just that's a quick flavor of what Celestial's doing, and some of the things that we possibly can work with industry partners on.
Thank you very much, Subal. We are always amazed of the developments of Celestial AI. You are really breaking the memory wall and really pushing the photonics technology as, in my opinion, has never been for many, many years. So congratulations. Today, you show 115 terabit per second switch with a 33 terabyte unified shared memory. How does this compare to the electrical fabrics?
It's a difficult question to answer because I would say it's of the same order because it depends a lot on the exact network topology. So especially, okay, let's start about the switching total switch bandwidth, right? Because here we're showing one layer of switching through a very simple all-to-all connected network. Of course, different scale-up technologies use different network topologies, right? So it's a hard thing to compare. In terms of memory, definitely this is something that, there is no other disaggregated memory platform of this nature where you get, full HBM bandwidth through an optical platform, right? So there is no other optically enabled HBM solution out there that, as far as that we are aware of. Of course, there are other memory platforms that you can use that are CXL based, but those use PCIe, and so the bandwidth is actually, much, much smaller than what you can get through direct HBM. So, and of course, the reason for that is HBM is, very fast electrical serial interface, and so the range that you can put a chip is a few millimeters. So unless you give it an actual optical interface, you can never get the disaggregated performance that we have here. So that's definitely very unique, I think, at least in my opinion, to what we're doing right now.
It's very unique, and also congratulations on using the right packaging for scaling up. This is really what is future proof. We have a lot of questions for you. Let's start. Matt Singer coming all the way from Thor Labs. It was great to see you in Malaga last week. Matt, what's on your mind?
Yeah, thanks so much for the really interesting talk. So one thing that was mentioned a lot in Malaga was, getting light on and off of the chip. So you mentioned standardization of these fiber connectors. I'm just curious what type of connectors you are currently using, what you're leaning towards. I, have a lot of, work with the fiber team at Thor Labs and just working on different modeling and how do we, help designers get light on and off of these chips. So I'm just curious what you think about that.
Yeah, so we actually have a design that we kind of built from scratch. So okay, let's step back. So it's essentially, so we use a gradient couple platform. As Liron said, we believe the same thing in that you need surface coupling out of these packages to really get to the highest densities, because you do indeed need 2D fiber arrays so that you can use both axes of the chip. So that's what we use. So we actually have a bespoke solution that we have made from scratch. And then we're also working with industry partners that are working on similar programs with other companies, and they're all sort of different, right? So at the most fundamental level, there are expanded beam connectors, which that turn vertical coupling into a horizontal insertion extraction sort of mechanical model. But that's sort of the problem, right? I can't describe it any more than that. In that, that's the boundary condition.
Subal, you did say a lot between the lines, so thank you very much for that. And indeed, Matt can really help you because he's actually an expert on nanophotonic coupling. So if you can even reduce the losses more, it's because Matt can have good ideas for you. The next question comes from Stein Kuipers from Ligentech. Stein, what's on your mind?
Hello, thanks for the presentation. You mentioned that you are currently using electro-absorption modulators. Do you see a role for more advanced materials based on electro-optics for these kind of PICs in the future?
Absolutely. So I think the requirements for modulators can actually be summarized very easily, right? Yes, they have to be very compact, right? They have to be very low energy consumption, but the compactness normally goes very hand in hand with low energy consumption if you lower the cap. So advanced materials, definitely plasmonics or even polymers. We've seen a lot of data recently, even at ECOC, and some very good results there. And then finally, we think thermal stability is a very key part of it. And so rings, we think, have a weakness there that in future integrations might be a problem. But you can always build MZIs with more exotic materials, and as long as the reliability is proven, I think there's definitely a role for them to play. Sure.
So Subal, you're not going to tell us if you're using 3.5 or thin film lithium niobate, or you're not going to disclose that. You cannot.
No, we cannot. But
Subal, next question is coming from a company that can help you doing even faster. We go to Polariton and their plasmonics. Stefan Koch, what's on your mind?
Yeah, thank you, Subal. My question goes to WDM operations. I think you mentioned you have implemented a system before, lambdas. I would like to know your opinion about going to more colors, 8 or 16.
Yeah, so 8 is on our immediate roadmap. So the 4 lambda actually has been developed for several years. So we expect something even next year to come out that's 8 lambda, and then wavelength is absolutely the quote unquote easiest way of scaling this. The other things, again, Liron, I think, did a good job pointing that out, that they run into brick walls pretty quickly. But we absolutely believe the same thing, that wavelength scaling is very critical.
Subal, congratulations on everything that you are achieving. I would like to say that Celestial AI, from the very beginning, since they joined Optica, they have been open for collaboration. So if you have solutions or particular room for collaboration, please contact Subal privately or contact us and we'll make the introduction. Thank you and see you very soon, Subal.
Thank you.
Let's move on and go to the next one. The next presentation is very important because it's about collaboration. We are bringing together two companies who have found reasons to work together. I'm talking about Ipronics and ANSYS. What we are doing here is to understand how we can help Ipronics, a company in the programmable photonics who has found their application as being the enabler of next generation OCS. Daniel Perez Lopez, founder of Ipronics, thank you very much for being with us. The attention of everyone is yours.
Thank you, Jose. Yeah, it's a pleasure to speak here, and especially together with ANSYS. I'm going to speak about Ipronics and the solution that we have built during the last years, talking specifically about a topic that has appeared already in this industry meeting, optical circuit switches, but in our case, based purely on standard silicon photonics. I think in the last presentations, we have seen very good motivations about why innovation in the networking side is a must-have. We have seen in the past events how GPUs integration density within a cabinet are pushing the limits of the actual power consumption intra-cabinet that is allowed to have, the power consumption of the overall data center, how the industry is actually pushing those limits, trying to put more and more GPUs within these type of cabinets. The vision that we have is that moving forward and also talking to the industry, we have seen that future networks are going to be hybrid networks. I think that was mentioned as well in some of the presentations today, where we are going to see the coexistence of very different part end nodes pushing data from GPUs and accelerators to the intra-network of the data center. But at the same time, we are going to see hybrid networks in the sense that we are going to see the coexistence of electronic packet switching with and assisted by optical circuit switches in some part of the region. We have seen that these applications are mainly related to topology reconfiguration. Today, so far, what we have is a general purpose networking for an heterogeneous amount of problems. Problems that I'm referring to is not the same that you are doing LLMs or different type of computations, then you will require to have the network adapted to each specific problem. So the vision that we have at Ipronics is, okay, we are putting one of the tools that are going to be necessary for the toolbox of future data centers. And in our case, as you can see, we have built a solution based on standard silicon photonics. We are taking probably the most conventional and simple component, the match center interferometer. We have put thousands of those into our silicon photonics solutions. We have built the control electronics on top, the software, and since last OFC, we are sampling to customers already our 1U rack 32 by 32, both for scale-out applications and scale-up. The key asset that we bring is, of course, the silicon photonics device. You can see here an animation describing the reference design that we have put on the market, how complex this type of silicon photonics can get. I think that we are talking about the state-of-the-art solutions in terms of component integrations. We have started with a 32 by 32 that already finds applications within the data center, but we are multiplying by 2 every single year the radix of our solution. And also we have another asset to allow us to even expand this radix requirement. We are leveraging on standard photonics, standard silicon photonics. How can I describe this? We are seeing similar progress in the overall ecosystem, most of them optical members, where we are seeing foundries, OSATs, material providers, fiber array providers, process providers, working together to actually leverage on an ecosystem that can rely now on larger scale photonics. And in our case, larger scale means large-scale programmable photonic solutions that allows us to have thousands of photonic actuators and make them work cooperatively in a way that can provide solutions to the market. In our case, through optical switches. I just want to finalize saying that the device that we have created, this OCS, it's specifically purposed for the data center operation, for the AI infrastructure, meaning that it's designed for the full O-band capability. So that means that it's designed for transparency. So pluggable transceivers, near package optic solutions, optical interposers, could be basically integrated and interconnected through our solution. As I said, we believe on a future of heterogeneous coexistence of multiple different devices in the data center network. OCS brings is not an apples to apples comparison to electronic packet switches. It's there to complement the network. So that's why we have built this multi-platform, multi-format solution able to handle different type of traffic. The key differentiation of Hyponics is built on standard silicon photonics, reconfigures in sub-milliseconds. There was a question before around this part. And definitely there are applications that are pushing for this. Some players has already figured out how to solve the key bottlenecks that prevented this to happen. And being sub-millisecond reconfiguration time is the sweet spot for some of the applications. I would like to finalize with a comparison with power consumption. The power consumption of our silicon photonics, even though we integrate thousands of these phase actuators, the actual consumption of the peak per se, the photonic integrated circuit is less than 3 watts in the worst case, plus the solution that we bring, which is lossless across the O band, thanks to per channel amplification, or only consumes less than 1 watt per active channel, which is comparably low with an electronic packet switch solution. How we have been able to do this? We have many verticals of improvements. One is on the circuits level, on the system level, but another one is on the component level. And I think that's perfect to give the floor to Ansys, which has been a wonderful partner assisting us to reach there.
Well, great. Thank you. Thank you, Daniel. I appreciate that introduction. And so, before I set the stage to talk specifically about what we've done in support of Hyponics, it's been a great collaboration. Just wanted to introduce the platform that we have at Ansys. So Ansys really does have a multi-physics, multi-scale platform for simulation of optical components. Lumerical is the main set of tools that are used for photonic design, but we also have tools for optical component design at ZMAX, and then if you advance, Daniel, to the next slide, to be able to do more system level simulation and rendering using our SPIOS tools. Specifically for the application and the use case that Hyponics was interested in, we really needed to be able to support them with a multi-platform solution for PIC design. And so this is just a schematic that just illustrates the different solutions that we have with our Lumerical toolset at Ansys to be able to do design all the way from integration with layout tools to be able to integrate layouts that are created with those tools into the component level modeling, being able to do really robust physics enable component level modeling using algorithms like finite difference time domain or electromagnetic mode solvers, being able to then generate compact models out of those component designs, I should say, to be able to bring those into circuit level simulation, and then finally be able to take those out for design rule check, verification, and finally tape out. So really, with the tool set that we have at Ansys, we have a full ecosystem support for PIC design. Daniel mentioned this key need to be able to investigate new complex component designs using our tools. And so there's been a lot of effort put in over the last several years, but I would say even more recently on our so-called inverse design capabilities, the ability to actually design photonic components with large numbers of parameters to achieve specific targets. In this particular case, looking at example where we're looking at designing a coupling system with minimum insertion loss and also being able to minimize the polarization dependent loss. And this was just an example to demonstrate the power of the tool for being able to do inverse design, designing a coupling system with over 3,000 parameters, using our GPU accelerated solutions to be able to get solutions in under a day. If you move to the next slide, one of the other big advances I think that we enabled for Hyponics was the ability not just to optimize these systems, but to connect optimized workflows together through automation tools. And so you can advance through all of this, Daniel. But basically, we have a tool at Ansys called OptisLang, which is a machine learning based software solution that enables both automation of workflows between different algorithms that we have available, multi-physics solutions, but also uses machine learning to be able to do sensitivity and robustness analysis. So, Erman, for example, highlighted the idea of reliability analysis. This is just touching the surface of that, but the ability to really understand how, for example, manufacturing errors, alignment errors, how different parameters, the robustness of different parameters will impact the performance of that system. And so you can get really detailed insight and analysis from that in a really streamlined and automated fashion. And then finally, I think on my, so this just talks, about an example of using that OptisLink solution for the design of a modulator in a photonic circuit, just going through the full design workflow from component to circuit, being driven through an automated workflow using our OptisLink tools. And then finally, in the last slide, one of the other key points that I think is key as you're trying to bring these systems to scale is the ability to do large number of computations in a distributed manner. And so the tools that I've been talking about are cloud enabled. We're able to deploy these across large GPU clusters. And just on the right, what I'm showing are examples using, for example, NVIDIA GPUs. As you scale up to larger and larger machines, the kind of design size and the kind of scalability that you have with our solutions. And I think these, all of these things that I touch on were very valuable simulation solutions that we were able to provide to Ipronix to help them to get to market with their solution. So handing back off to Daniel to finish that out.
Yeah, thank you. Yeah, I just want to stress that part. As I said before, having these building block specific simulation, fabrication tolerance, or firmware design workflows has been a key asset for us. And this has been one of the key elements that is allowing us not only to provide what we are sampling to customers today, this 32 by 32, but also developing the building blocks already for a 128 by 128 solution. So the key summary is the usage of silicon photonics, and particularly the standard silicon photonics, is allowing us to develop the most cost-effective, mass producible system that is already achieving all the data center requirements. Thank you.
Daniel and Sanjay, very impressive work together. I'd like to hand the floor back to Liron Gantz from NVIDIA to voice a very important issue based on Daniel's talk in the chat, and then ask a question to answer.
Yeah. Thanks. So first of all, as I've written in the chat, I haven't talked about this, but there is a great importance in increasing the radix of switches. So radix is essentially the number of ports that a switch can output. And as the higher the radix, the flatter the network. And if the network is very, very flat, it doesn't need a lot of hierarchies, then we save twice. We save number of switches and we save power because we reduce the number of switches. So there's a great, I think this is one of the main issues that optical circuit switching can come into play within data centers. So that's my remark. The question, so I have a question for Ansis, and I've looked at your inverse design solution, very exciting, and very exciting that you are using GPUs. Is your inverse design uses the adjoint method?
Yes, that's correct, Liron, right? So it is basically using just that, the ability to just do one forward and one backward propagation to be able to then do iterative optimization of the design.
Thank you.
Fantastic. Thank you so much both. With time moving on, I will ask people to ask the remainder of your questions in the chat to Daniel and Sanjay. So we'll move now to Mark Rushworth from Finchetto, co-founder and CEO. Mark's team is developing a fully optical packet switch aimed at slashing data center power and latency, an approach that routes packets in the optical domain instead of converting back to electronics. Mark, please tell us more.
Thanks very much, John. And hello, everybody. My name's Mark Rushworth, co-founder and CEO of Finchetto. We've heard from a couple of people about optical circuit switches, and we've heard about microsecond reconfiguration times. when we started Finchetto, we looked at what the issue was and determined that the issue, the bottleneck, was actually the electronics and the speed of the switching, which is something that and you talked about earlier. And we thought to ourselves, well, what is it? What is it that can be faster than the electronics? And the answer was light. Light is the fastest thing we have. So our technical leap is that we actually switch light with light. So we eliminate the electronics from the switching control entirely. We switch light with light. And what that does is it gives us three aspects. It gives us lower latency, it gives us lower power, but it also gives us the ability to switch at line rate at the resolution of packets. So what we are developing is actually a packet switch to take on the layer 2 plus electro-optical switches that exist today. Now, what that means directly, Liron, to your point about higher radix means lower power and lower latency, is if we stay in the optical domain, because we're an all optical packet switch, we go up and down a spine and leaf network without going into the electronic domain, which means that you naturally get a higher radix. So that's what we're developing. And what are we targeting as the reason for developing it? Well, it's much like people have talked about before, but I'm going to sort of conceptualize it in a different way. We're targeting power, we're targeting efficiency, and we're targeting scalability. So on the power side, you've probably seen a load of charts of the power consumption of data centers going up and to the right, and it's going pretty fast at the moment. I've got a different chart here from Bloomberg, actually, and this is the change in electricity prices between 2020 and 2025 near data centers in the US, an increase of over 260%. Okay, and actually, harking back to something that many people have touched on already, picojoules per bit. If you look at that from a supply chain perspective, a supply and demand perspective, at the macro level, the way that I look at it is that position, so commercial or strategic position in this world that we operate in, is directly equal or exactly equal to the amount of compute you can do for the amount of power you do it for. So there's a huge foot race on at the moment for hyperscale data centers and other data centers to get access to power. Now, I'm not here to tell you that if I give you a low power switch, that everybody's going to be super sustainable. They're going to use exactly the amount of power that they can get their hands on, and they're going to use it to do more compute. So what that practically means with Finchetto's solution is we model that we can offer a single hyperscaler a 90% power saving across switching, and by eliminating lots and lots of transceivers, optoelectronic transceivers, that means that we offer on the electricity costs over 250 million in OPEX savings, which for increased compute means around 350,000 incremental GPUs. That's on a single hyperscaler. So that's the problem that we're solving on power. On efficiency, Erman, you talked about this before. This is something that Meta said just over a year ago. A single transceiver or GPU failure in the AI networks reduces the efficiency of the overall network by 40%. Times will have changed. The life is moving so fast at the moment, but that gives you an indication of how material it is when there is an efficiency problem and a hardware issue in the network. You can solve that in software, but it takes up to 10 minutes to solve that in software. You can solve it for more performant hardware, so better SFPs that don't break down, or you can solve it by eliminating or reducing the number of failure points in the network, which is what we're doing. So by taking the network all optical, we're eliminating those electro-optical conversions, we're eliminating the number of transceivers. Not entirely, you have to go into the electrical domain eventually, but in the layer 2 and above network where we operate, we're eliminating that conversion. So 82% of SFPs in a single hyperscaler network are eliminated, which saves around $1 billion of capex and retains still a 5 million unit opportunity for SFPs in a Finchetto network. And then third is scalability. There is no way that a hyperscale data center is going to throw out all of their Cisco, NVIDIA, and other brands, which I should have not mentioned the first two. But there's no way that they're going to throw out all of that existing infrastructure. So it has to be interoperable. Whatever we create has to be interoperable. A full rip and replace will not work. So what we've developed is a concept of an edge node that allows concrete integration and interoperability with existing infrastructure. And that's where there exists a layer 3 router opportunity for partner. Just to give you a bit of a flavor of previous work that we've done, we did some work in collaboration with British Telecom in the UK, part of a government-funded initiative, and we manufactured, we prototyped a telecoms wide area network product. We demonstrated the core capability of switching light with light at the resolution of packets. So in the wide area network, this is sub-lambda switching or fractional switching, and it consumed 12 watts of power for a 2x8 ROADM. So if you consider that in comparison to a packet-based router from the likes of Nokia 7750, that's a 99.8% power reduction for that line. Now, this is of interest to everybody who mentioned the 200 gigabit single lane issue. One of the things that we found when we delivered that prototype in collaboration with BT is that when we switch using our technology, we actually reshape the eye diagram, we reshape the data, which means that on the left-hand side, you can see an eye diagram, which is not switched. It's a pass-through our ROADM. And on the right-hand side, you can see a drop. So it is switched using our technology. And you can see the cleaning up or the reshaping of that data transmission line. And I think there's an opportunity there to partner specifically on the single lane 200 gigabit per second in the datacomms world to alleviate the burden on DSP, as Man was talking about before. We've won a number of awards, which I won't go into, but in amongst them, there was the Europas, which was a really big award for us, hottest pre-seed last year in Portugal, in Lisbon. And so, listen, if anybody has any questions, please shout now. And if anybody wants to talk to us about partnership opportunities, then please do come forward. Thank you.
Mark, thank you so much. You mentioned the collaboration with BT. So where are you with your sort of first deployments, and what do you need from this community to help you get this out there?
Well, I think the truth is, and probably everybody knows this, but the truth is that actually first deployments, where the industry is moving fastest is in the data center. It is in the high performance networks that are being built and being scaled out. It's probably not in the wide area network. It traditionally teleco has sort of pulled through from data center for the last 10, 20 years. So that's where we're looking to. But what we did as part of that BT project is proved several elements of our technology: the switching light with light, the ability to switch at line rates, and therefore target packet switching in the datacomms network, and the ability to reduce the power consumption massively.
Great. I'm going to pass you back to Liron from NVIDIA. Liron, you have a question.
Liron, hi.
So very nice results. So is this optical filtering a byproduct of the switching, or can you reconfigure this sort of optical filtering?
So let me try and unpick the question. If we are switching data, the reshaping or the cleaning up of the signal is a byproduct. It's a natural byproduct. Now, as it turns out, in the ROADM use case, in that add-drop multiplexer that I showed that generated that result, you have two paths through the switch. You have a pass-through where you don't activate any switching mechanism, and you have a drop, and there you activate a switching mechanism. In the datacomms network, so in our 48-port switch that we're building out at the moment, you're going to go one of 48 ways, and so you necessarily switch to go one of those 48 ways. So you will always have that byproduct of cleaning the data signal.
Okay, thank you.
Okay, great. Thank you so much, Mark. Let's move to welcome Chris Maloney, Managing Director, US Operations and Director of Business Development at VPI Photonics. Chris represents a team known for system-level code design. So we're zooming out at the end-to-end system, see what actually ships reliably at scale. Chris, the floor and attention of everyone is yours.
Hey, thanks for the introduction, John. If you're not familiar with VPI Photonics, as John mentioned, we're providing photonic design automation solutions for just under 30 years now. So some of the data center applications that we're talking about today range from the HPC infrastructure. So you've been hearing about WDM systems, photonic integrated circuits, co-packaged optics, but also data center interconnect. So connecting data centers together, short reach IMDD systems. We also support in our software, electrical optical co-design as well. And also we support applications for optical transport. So high capacity, coherent systems, multi-core fibers. So the terms you're hearing, scale up, scale out. I also heard, I think a couple of weeks ago, scale across for optical transport networks. So there's more and more vocabulary to learn. But yeah, our solutions, they really allow you to design across the entire photonic, design workflow. And one unique perspective that we take that John mentioned is we allow for more system level PIC design. So we do have tools at the device level for designing your couplers, your waveguides, what have you, but also your photonic integrated circuit. So in a schematic-driven environment, wiring those different devices together to achieve some result that would then be used in your full optical transmission system. So really the idea is that you can start with your system, understand what are the requirements that are necessary, and then go and design your PIC that solve those requirements and also take into account the different compensation strategies like DSP or forward error correction or DFE. So really the problem we're trying to solve is, simplifying the design complexity that comes with this. So you're working with your PIC designer, you're working with your optical systems engineers, and you want them to work together seamlessly and allow them to optimize their PIC for the system performance. So I'm showing a schematic here that actually is very similar to what Liran from NVIDIA mentioned early in his presentation, showing a WDM system using silicon photonics microring modulators. So if you just kind of look through the schematic, we have an array on the left side, an array of 8 lasers, different wavelengths. Those are multiplexed together. And those pass through an array of microring modulators, all with some electrical signaling being driven by this PAM electrical driving source. The signals all have to pass through a single mode fiber. They get demultiplexed using these 3-ring filters. And then they all pass, all those different signals pass to adjacent receivers. So you have your photodiode, feed forward equalization, maybe DFE, and then you want to do some analysis, some bit error rate or T-DEC-Q or I-diagram analysis. And so that's what our system level tool allows you to do. But within that, in this hierarchical nature, what we're allowing you to do is design your photonic integrated circuit and actually optimize it for the system. So at the end of the day, you might a lot of people might over optimize their PIC, not taking into account the DSP or feed forward equalization or what have you that might compensate for some of the impairments that exist. So this is really what we're enabling, is allowing you to design your micro ring modulator or your 3-ring filters for full system level performance. And just on that note, feel free to reach out to me. I'll also be at the PEC event next week in Sunnyvale if anyone wants to connect in person. But yeah, thanks for the time today.
Great. Thank you so much, Chris, for joining and showcasing VPI Photonics Design Suite. Keep questions for Chris in the chat. Please do direct them. In the interest of time, we are going to move on. So please welcome Kees Propstra, VP of Global Sales and Marketing and General Manager of Quantified Photonics USA. Now, of course, part of Teradyne. Kees helps customers industrialize photonics test. Kees, please take it away. Thank you.
Hello, everybody. Greetings from not so sunny California right now. Thanks Optica for organizing this very insightful webinar as usual, and it's great to see the amount of photonics innovation. And what all these presentations have in common is that these next generation technology will depend on photonic integrated circuits. So that's obviously kind of new for us. We're going to scale these photonic IC technologies to ultra high volumes. And, we are basically, as a company, specializing in test strategies for scaling photonic IC technology. So the manufacturing process is really important. We go from wafer, die, multi-die, optical engine, to a CPO switch. And you need to really test your device, at all these test insertions, at all these different stages, to be able to produce a product that is meeting all these specifications. So obviously, that's a big challenge. There's a couple of areas, and unfortunately, we don't have a lot of time, but that I want to mention. So shift left, meaning you test as early as possible in the manufacturing process to weed out potential failures. So you do a lot of testing at wafer level, but you need to still do some additional tests, of course, when you start integrating, because you change your configuration. So shift left is very important. Test a lot early in the process. And what I call is the testing funnel. So test a lot, again, early in your product life cycle, meaning that if you get a lot of insight early in the product life cycle, you can basically scale down your testing to really start optimizing your test methodology, your test plan, to drive high volume manufacturing. So that's really important. Those are really important elements. And the way we see this evolve, there's kind of 4 pillars where we believe we can play a big role in this ecosystem. So first of all, combining optical test function into a bigger test system to characterize devices over wavelength, over polarization, LIV curve, RIN measurements, to really expedite DVT as part of this testing funnel, testing early in the product life cycle. We need to have new products, test instrumentation, like high power lasers, a lot of requests for that, to distribute that over multiple devices, ELSFP modules, multi-channel, multi-wavelength lasers. A few people talked about it, to power up your PIC, also as part of a testing approach, obviously. And then high density optical power meters. If you can test hundreds of channels simultaneously, that will obviously really speed up your testing. Then on the other side, we need to have photonic IC ATE testers, really like big iron ATE testers that we see for semiconductors. We also need to have that for photonic ICs, and that includes optical instrumentation, that includes probing, of course, to get access to your signal. And then last but not least, we have these really high density optical modules like CPO, optical engines, that really need to be tested at speed prior to usage in the network, prior to deployment. So testing high-speed I/O in parallel is going to really relieve a big bottleneck in this approach. So it is really a new paradigm that I see. So we're talking really about ultra high volume manufacturing of PICs. So it's not just about the cool photonic technology, but it's also really about testing this in high volume, focus on cost of test, not just CapEx, look at operational expenditures as well, parallel testing, reducing test time, high density test instrumentation. Obviously, it cannot be too bulky. It needs to be streamlined into a big tester, and purpose-built test instrumentation, not like R&D equipment, but it really needs to focus on DVT and high volume manufacturing. So in general, obviously, saving money, improving yield, minimize waste by doing these test insertions smartly, so that you weed out failures at the right point, and equipment uptime. So completely different conversation. I always say the dark side of the moon, where everybody wants to talk about the cool photonics hot chips, which is really cool. We all love to talk about it. But there's another side of that as well. It's really being able to manufacture this in high volumes. So you need to have the equipment, the testing infrastructure to enable that. So that's what we specialize on. And of course, this is all about partnerships. We work with probing companies. We work with a lot of the end users. And it's very exciting to be in this industry right now. Thank you very much.
Thank you very much, Case, for being with us. Thank you for your great demos at ECOC, and I can't wait to see you at OFC. I know you have something very big preparing for us. Stay with us because the next two presentations, Qant and Lumai, can really use your technology. Let's go. Let's move to the next company. I would like to welcome to the stage one company that has really been making a difference by doing photonic processing. And in this field of AI, they can really revolutionize the industry. Matthias, thank you very much for being with us. Let's welcome to the stage Qant.
Yeah, hello. Thank you for a warm welcoming, and yeah, it's really a pleasure to be here, discuss with you the, let's say, possibilities that we can explore in the scope of AI enabled by photonics. I hope you can all see my slides now.
Exactly.
I just want to start with a short introduction of whom we are, basically, Quant. Can you do my slides change?
Next slide.
Seems that there is a problem despite testing it beforehand, so give me a second.
In the meantime, I would like to encourage everyone to use the chat to interact privately with one another. I'm getting lots of WhatsApps from all of you saying that you managed to make a business connection over the last 96 minutes. So thank you very much for that. This is the best thing you can do for us, connecting in a meeting. Matthias, how are we doing?
I hope it's working now.
Let's go.
Can you see it again?
I see the first slide. Let's go to the second one.
Somehow it does not change. It changed on my screen, but not on the shared one. So I'm sorry, but it was working before. Now it should work. Okay, perfect. So yeah, we at Quant, basically, we are a company based in Stuttgart. In principle, we are roughly 100 people now. And we are really dedicated to photonics, especially for photonics for AI. So in principle, just as a company that is deeply rooted in tech, we are pretty young, but if you want to sum up, we basically have about 900 years of industry experience now. But we have heard today that basically a lot of, let's say, proven technology comes to its limitations in the scope of the race for AI compute. We are convinced that it's not only true for interconnects and like shuffling around data, but also for the compute itself. In principle, not long ago, with each generation of new CMOS technology, we have seen also improve in efficiency of compute itself. However, that's not true anymore. Furthermore, we also have the, let's say, limitation of only have a couple of suppliers for these, let's say, chips that you can use. And in conclusion, we are convinced that there is a window of opportunity to have, let's say, completely new approach and new technology. That's basically what we're talking here. So Quant was actually founded in 2018. It's dedicated to basically thin film lithium niobate as a working material. And we cover the whole value chain from wafer to basically complete compute systems. And to summarize, in principle, we're currently in a state where we have our first working prototype coprocessors dedicated for AI applications. And we are really proud to have the world's first coprocessor offering 99.7% accuracy and being sort of like the first processor that can work in the required customers, customer requirements of a data center and is seamlessly integratable with an AI stack. So in principle, the question is, what can Quant offer and what we basically need to scale this amazing technology further? First of all, you can, of course, already buy these kind of processors as an early adopter. And the other parts are we have a PDK for thin film lithium niobate photonics, and we offer that for potential collaboration and also multi-project wafers in collaboration with our partner IMS Chips here in Germany. And what we're looking for is to be able to actually scale up to even bigger systems. We look for partners for all sorts of integration. I think I'm happy to discuss these options with you now.
Thank you very much, Matthias. You just announced 62 million euro round. So how are you going to spend the money? What is the next thing coming to Quant?
Well, in principle, I think, so we are basically following up on what we have done. So in principle, we're trying to do basically the next generation of these kind of native processing units in native processing servers. And in principle, it's a close collaboration with our first customers to see where are these systems for which kind of applications they prove beneficial, and then tailor-made the next generations to fulfill these market niches.
Well, what is the main value using thin film lithium niobate? Because we have seen at ECOC that there's a huge explosion of foundries all around the world bringing to the market TFLN. Why did you decide that TFLN was the material system for quant, and not only because you can produce it?
Well, okay, so in principle, as I've mentioned, so we try to do basically the whole stack from the material to the full system, and we have concluded for our requirements to provide the customers with a AI specialized accelerator, like photonic accelerator. Thin film lithium niobate offers the best compromise of all the requirements you have to make the system performant. So in the end, you have to basically outperform the CMOS world, and we are convinced that lithium niobate is the way to go.
Congratulations, Matthijs, and the whole team of Quant. It was a pleasure coming to visit you earlier this year, and it is a pleasure to witness the success of your photonic accelerator. If for any of you who want to see how the entire system works, I have a fantastic video in my LinkedIn. Matthias, thank you very much. And let's go to the final speaker today. We always try to keep one big thing coming to the industry for the end of these online meetings, and today we are really happy to welcome Loom AI. We are welcoming them with their CEO and co-founder, Dr. Xianxin Guo. Thank you very much for coming today. It is great to see how 3D optical computing architecture Loom AI is making such a big impact on the industry. The floor and the attention of everyone goes to Loom AI.
Right. Thank you. Thank you for having me here. Let me share.
Thank you for being here.
Does it work?
Yes, it works. Maybe you can go to full screen. Yes, now it's fantastic.
Yeah. Hello. So I'm Xianxin, CEO and co-founder of Loom AI. We are also working on optical computing, and we are some quick background here. So we are a spin-out from University of Oxford. We are based in the UK. So our team combines basically world-leading experts on optics AI and also very seasoned engineers, electronic engineers. For example, our head of engineering, Enzo, our head of product, Phil, both of them have more than 20 years experience working with semiconductor. Even though we are an optical computing company, we are still actually relying heavily on electronics. So clearly, we are targeting this huge and massively growing market. And today, the compute is growing as fast as we can imagine. Right now, we are at a point that basically power is the single biggest limiting factor, and we all understand this. So, but what I want to point out is actually, if you look at the data centers, the power consumption, the lion's share is actually still with the IT servers, the IT equipment. So that's why we are using optics to solve the compute problem rather than like data movement. So when we look at optics, naturally we see lots of these unique features that make optics not just like good for interconnect or communication, but we can also use them for compute. It's like ultra low power consumption and lots of ways for us to process information in parallel at high speed. So all of these nice features basically are very attractive, and therefore there are like lots of attempts to build optical or photonic processors over the past few years. But clearly, we heard about this concept for many, many years, and we still haven't really seen a very good optical computer in our real world yet, right? So left-hand side shows a very typical example of a photonic chip that you can use it for processing information. Basically, a few very fundamental technical challenges basically are there. So first, usually the photonic component footprint is very big as compared to electronic transistors, which leads to a very low compute performance. So the performance gap between existing photonic processors and like digital processors are still huge. And then we usually also struggle with like high optical loss or high accumulated noise when we use optics to do the analog compute. And a very important issue is also when we need to get the data in and out from the optics, connecting the optical world and the electronics, right? Because we do need to think about the laser and the driver chips and the amplifiers. all of these things can easily negate the benefit of optical computing. So overall, these are like very fundamental technical challenges. And so people try this idea, build different systems in the lab, but it just doesn't seem to work. So at Lumai, we are solving this problem with a 3D optical computing. So this is not a new idea as well, but the architecture works really well for us. So by using the actual 3D optical computing, we can actually perform millions of parallel operations in a single clock cycle. And this is very important because now we can do massive amount of compute. And once we are into the optical domain, then we can basically amortize the conversion cost by doing more and more compute per conversion. And in this architecture, for example, if we can build a very realistic optical matrix size of 11,000 1,000, we can basically perform 1,000 compute per conversion effectively. Then we are significantly reducing the power consumption cost and also the system cost as well. So basically, the 3D computing approach is massively scalable, and it solves lots of those fundamental challenges that other methods couldn't really solve. And we are not building a fully optical system because today we still need to rely on digital electronics a lot. We believe that the future compute should be heterogeneous. So in our system, we use both digital electronics and also optics as a complete AI processor. So the digital processor ensures the compatibility and managed memory and interconnect, and also interface with the software stack. This makes sure that actually when our optical processor is deployed in data centers, people actually don't need to worry about optics. They don't need to learn optics. Optics is just a hidden box, but it performs the matrix math extremely fast, extremely energy efficient. So because we can solve the energy efficiency, we can significantly improve the energy efficiency of compute. This leads to a significant reduction of the total cost of ownership in the data centers. Because basically today, once again, power is the biggest limiting factor. So a few years ago, all of these were just ideas. But over the past 2 years, we have demonstrated the technology. We have significantly improved the scalability. And now we are actually, as you can see, this is an actual server box that we use in the lab. We are rapidly matching the digital performance. So we design our digital core and we design our optics. So overall, our compute speed today can reach over 100 tera operations per second. And this is basically comparable with some really good digital processors. So this is the first time that optics or any analog processor can actually come close to a leading digital performance. And this is very important. Then in another 2 years, then our optical AI processor will achieve energy efficiency advantage over digital processors for the first time. And that can be also tested and deployed in the actual data center environment. So we have been talking to lots of industry partners and potential customers. We target compute-intense workloads, and therefore, naturally, we focus a lot on AI inference, and we also can support like solving optimization problems and some other scientific computing as well. So finally, a bit of a background on us. So we are VC-backed business. We raised over $30 million funding, and we have been running actually with pretty good capital efficiency. And we will open our next round in Q1 next year. So if there are any investors here that are also interested in us, feel free to come to us.
Thank you very much, Jianxin. Actually, many of your investors were in Malaga last week, and your company actually sounded many times. You're one of the ones to watch. Couple of questions for you. The first one is single clock cycle computation at gigahertz. What's the limiting factor? Is it the optics or is it the electronics?
Electronics. So
I was
optics
expecting
clearly.
that. How fast can you go? How fast can you really go?
So we are basically a believer of the slow and wide approach, to be honest. Once again, if you calculate the energy efficiency of the whole system, then it makes more sense to use more and more parallel channels to compute. This helps us a lot. Therefore, we are not keen to use 100 gigabit per second transceivers per lane. So we are basically maintaining moderate data array for now, and that also simplifies our electronics.
Xianxin, in 2025, you have the testbed. In 2027, you deploy. So what has to happen between these two landmarks? And most important, how can companies like Polariton, Heteromerge help you in this development?
So what I didn't mention is that actually we need to use lots of optical and photonic components in our system, integrate them into a functional complete system. So for example, right now we are looking at different kinds of light transceiver solutions, and we are designing our own optical transmitter receiver solutions. And we also need to use very good fiber coupling or chip coupling solutions as well. So actually we talked to some of the suppliers here in this meeting as well. So overall, if you have very good transceiver solutions, if you have very good connectivity solutions, or if you have other, say, very good free space optical solutions, then we are very open to talk to these companies on collaboration as well.
Thank you very much, Xianxin, and congrats. Many investors are contacting Optica asking about you. So congratulations on everything that you are doing, and congratulations all the speakers today. And also, most important, congratulations to the people that made this meeting free for everyone. Our sponsors, Ligent Tech, New Photonics, Peak Advanced, BPI Photonics, Polariton, Quantify Photonics, Axelink, and Vanguard Automation. Thank you very much. I'm gonna cut now the live stream, and afterwards those who want to stay for a networking session, a bar discussion, they can stay online also after the meeting is over.